Okay, so the first lecture didn't work out so well. The PowerPoint got washed out, so I'm doing it again, just for fourth period. Diffraction and interference. Start with diffraction today. So, diffraction is based on Huygens' principle, because Huygens realized that light acts slightly differently than just by reflection or refraction. Instead, he saw that light waves, they spread from a point source. They can be thought of, when they're spreading from a point source, like a light bulb or a candle flame, as overlapping secondary wavelets, just little drops. Each one have its own circular pattern, and when they add together, you get the wave front that we're used to. And you can put these droplets, these point sources, every point on a wavefront can be thought of it as its own point source for this purpose. As these wavelets spread, they combine and create straight or curved wavefronts. This is a pretty tricky concept, but it helps explain the next step that we really need to understand, which was diffraction. Diffraction is the bending of any wave by means other than by reflection or refraction. So anytime a wave bends, not by reflection or refraction, we call it diffraction, the diffraction. And we can see it best when light goes through holes. When light bends around corners, like when it goes through these holes, as it would because of Huygens' principle, I'll show that in a second, you get strange shadows. Through a big hole, you get a sharp shadow. But when you have a small hole, a small slit, you get a shadow that has a lot of penumbra and a bright spot in the middle. This is very odd and happens because of the process of diffraction. The light actually bends around these corners. The smaller the hole, the more diffraction you're going to get. So, diffraction is increased by the wavelength. The longer wavelength compared to the size of the object, with a smaller object, equals more diffraction. You can see this in this first picture, where you have long wavelengths with a large object. They diffract around it, but not completely, so you still have a shadow. Then smaller object, same wavelength, smaller shadow. With a tiny object, the diffraction actually combines back, so it actually casts no shadow whatsoever, because the diffraction is so much, it basically ignores that object. Now, if the opposite were true and we had small wavelengths, you create a much larger shadow, as they wouldn't diffract much around the edges of the objects. This can also be seen with radio stations. AM radio stations have a much longer wavelength than FM radio stations because they have a smaller frequency. FM have a larger frequency. So AM radio waves, you can get the signal much better than you can get the signal for FM radio waves. It's because the AM radio waves diffract around buildings and mountains and hills much better than FM radio waves do with their shorter wavelengths. Microscopes, however, are opposite. For a microscope, you need smaller wavelengths because longer wavelengths of light create diffraction on what you're looking at. You can see that here with this cell. The diffraction makes the image blurry. The bending of the light fills in spaces. Makes it so it is indistinct. You can see that. With a very small object and large wavelengths, you get something like this, where it's almost useless because it's so blurry. So the microscope, you want to use smaller wavelengths as you can. X-ray microscopes would be much more effective than visual light microscopes, for instance. We actually realized that the smallest wavelength you could possibly get is a single electron. So we use electron beams in what's called an electron microscope to measure the smallest things, to view the smallest things. It minimizes the blur you get from diffraction. Just a reminder, waves interfere. Interference is something all waves do. They create what are called interference patterns. It's when two overlapping waves, crest to crest, or crest to crest to trough is called constructive interference. And it gets twice as big, or bigger. You add the crests together. When you have crest to trough, or trough to crest, you get destructive interference, and they cancel out before they move through. In the standing wave, you can see in phase, double size, out of phase, cancellation. Now, when waves are going around in complete circles, like Huygens principle states, you see that they interfere in specific patterns. The dark parts are troughs, the white parts are crests, and the gray parts are neutral areas. This is a water tank, by the way. It's called a ripple tank. They're hitting the water, creating these waves in 2 points. So interference is important for diffraction because once a wave gets diffracted, these waves can start interfering with each other because they start to bend. Young scientists found this out with what is called a double slit experiment, or Young's interference experiment. He actually used pinpoints instead of slits, but slits work. You take two little slits and you cut them into paper, very small, very close together. And when he put monochromatic light, so light of one color, monochromatic means one color, into it, he got this, a spread out from diffraction. But when he put it through two slits, he got this pattern. Hopefully we'll see that in a few days with a lab or an activity. But you can see it's got points where the diffraction from the two different slits starts to interfere with each other. Points where they cancel out destructively, points where they add constructively, so get very bright. Actually spreads out even more. There's also what's called a diffraction grating. It's a common device. It is mini slits, lots of slits all put together, parallel to each other, very small. When you put them together, and when you put light through a diffraction grating, it splits into a rainbow. And that's because each diffracted wave is interfering with each other in specific frequencies, specific wavelengths, canceling out some colors, increasing other colors, splitting up into our 7 primary colors. A CD is a good example of a diffraction grating because the little grooves that store the information act as a perfect diffraction grating for when light hits it. That's why they shine all rainbowy, like this. A peacock feather. Peacock feathers are very thin pieces of feather next to each other, very close. They act like a diffraction grating, so peacock feathers create a rainbow effect. When light goes through them, it gets diffracted and interferes, creating a rainbow just like a diffraction grating. Hopefully this time worked out better. Tomorrow we'll try interference.